All right, we're going to be talking about solubility in ion equilibria. This is part of chapter 16 in your textbook. You will need a calculator. I would suggest the gold packet for solubility rules and some place to take notes. This is part of unit 7 from AP Chemistry, and here are the objectives that we will cover. We're going to start our discussion with looking at insoluble salts. The term dissolution refers to how a substance will dissolve here in water, and we've talked about solubility before. We talked about some solubility rules in the past, things like group 1 salts, like sodium, potassium, they're always soluble. Ammonium is always soluble. Nitrate, there are other things. Right now we're going to talk about lead sulfate. Our solubility rules will tell us that lead sulfate is insoluble. That's a very black and white view of solubility. Either it is or is not soluble. In reality, it's probably more of a grayscale. It's almost insoluble, but there are some ions that will dissolve. So I would say it's partially soluble. When an ionic compound dissolves into water, it is a reversible reaction that does reach equilibrium. And however many ions dissolve, it would dissociate into cation and anion. Here it's a 1-to-1 ratio. And we will do lots with this concept. We're really going to look at it in a quantitative way. The quantitative method that we use to look at solubility is through the use of a constant KSP, which is the solubility product constant. I'm going to set up a K expression, and we've seen K expressions before, where we set up the products over reactants. Here our products are aqueous ion species. Our reactant is a solid. We don't include solids in those expressions, and so our KSP is shown here. Equilibrium will lie far to the left because this is a slightly soluble salt. So very far to the left, KSP value is going to be very small, and here is the value at standard conditions, which is always 25 degrees Celsius. Why don't you go ahead and try writing the dissolution or dissociation reactions for these salts in water. You can pause, try that out. Here's what you should have. Calcium fluoride will break apart into calcium ions and fluoride ions. And to balance it, we would need 2 fluoride. So it's a 1-to-2 ratio between those 2 ions. Bismuth sulfide would break up into bismuth ions. Those have a charge of positive 3, and then sulfide has a charge of negative 2. When we balance this, we'll need 2 bismuth and 3 sulfide, so a 2-to-3 ion ratio here. So we're going to do an example calculation where we're going to solve for KSP, and typically KSP values, you wouldn't really solve for them probably. This is just something that we're practicing here. KSP values are standard, they're constant for each solid. So we're looking at copper 1 bromide, and the dissociation is shown here. And we're going to look at this with the use of an ice table. Since this is a solid, we don't include that in our ice table expression. These species are both aqueous, so they are included. We don't have any of them to start. Both of these are going to increase in concentration as the solid dissolves. And solubility, or molar solubility, is typically represented by the letter S. I just prefer to use the letter X instead because it's something that we've used for ice tables in the past. And my S's kind of look like 5s. So it's going to go up by X. This is going to go up by 1X. And so if we plug into a KSP expression where we have copper ions times bromide ions, it would be substituting here X for copper ion, X for bromide ion. And what we are given is that the molar solubility is 2 times 10 to the negative 4. So that is my X value. So obviously this is X squared. So KSP is equal to X squared. And so that value is 2 times 10 to the negative 4. And I will square that. And when you do that math, you will get 4 times 10 to the negative 8th. That is our value for KSP. We're going to do another example, very similar. Here we're going to calculate the KSP. We have the molar solubility here is 1 times 10 to the negative 15. And we've seen this solid bismuth sulfide in the example that we did earlier, where we broke it up into ions. All right, so our ice table, again, I don't include the solid. They both start at 0. This is going to increase by a factor of 2x due to there being 2 ions. Here there are 3 ions, so it's going to go up by 3x. So 2x and 3x represent the concentration of those ions. When we write our KSP expression, we're going to pay attention to that mole ratio. Whoops, that's supposed to be bismuth there. And I'm going to actually fix that. So that has a positive 3 charge. Due to the 2, I'm going to have to square this. And then we multiply that by the concentration of sulfide. And due to that 3, I'm going to cube this. If you recall, we use the coefficients as our exponents. And now I'm going to plug in 2x for bismuth squared, and then 3x for sulfide, and that will be cubed. So now I want to simplify this. So 2 squared is 4, and then that's x squared. 3 cubed is 3 times 3 times 3, so that would be 27, and then x cubed. If I simplify this, KSP is equal to 108 times x to the 5th. So I'm going to substitute. I know that x is equal to 1 times 10 to the negative 15. 1 times 10 to the negative 15. And I'm going to raise that to the 5th power. And so to solve, I've already done this calculation earlier to save time. I get 1.08 times 10 to the negative 73. It's a very small number. This is a very slightly soluble salt. Now, we've done 2 examples where we've calculated KSP value. What we're going to do here instead is that we are going to use the KSP value that is provided here, and we are going to solve for this solubility, which is the value of x. Again, we do not use our solid in the ice expression. We know this is going to go up by 3x, up by 2x. So this would be calcium cubed, phosphate squared, and now I can plug in my values for each of those. So that would be cubed, and 2x for phosphate would be squared. All right, 3 times 3 times 3. 3 cubed is 27x cubed times 2 squared is 4, so 4x squared. So again, KSP here, if this looks familiar, this is KSP is equal to 108 x to the 5th. And that was actually what it was before. So why is it the same value in terms of x? It's because previously we had a 2 to 3 mole ratio, 2 to 3, and so that's why we ended up with 108 times x to the 5th. Here we have a 3 to 2 ratio, so mathematically it's the same, a 3 to 2 or 2 to 3, and that's why we get 108 times x to the 5th. So now let's go ahead and finish this. That is the value for KSP in terms of x. We already know the value of KSP is 1.3 times 10 to the negative 32. That was given to us. Again, what we are solving for is x. So now I want to divide both sides by 108. And obviously that cancels here. That'll tell me that x to the 5th is equal to, in this case, 1.2 times 10 to the negative 34, and I calculated that earlier. Now, how do I simplify this? I want to take both of these. I want to find out what it is in terms of x. So I'll raise both of these to the 1/5 power, which would then cancel out the exponent there. So 1.2 times 10 to the negative 4 raised to the power of 1/5 gives me an x value of 1.6 times 10 to the negative 7. And that would be moles per liter, because what we solve for is the solubility, or the molar solubility. All right. What we have next, we're comparing 3 examples, and these 3 examples are all kind of similar. We're looking to see in which one of these is a concentration of hydroxide higher, which one produces more hydroxide ions, so it'd be more basic. We have the KSP value for each of them provided. Looks like the highest KSP value is for magnesium hydroxide. One thing I want you to notice, then all of these examples, it's a 1 to 2 ion. So when they dissociate, all 3 of these solids would produce the same number. They all produce 2 moles of hydroxide ions. So if we're looking at which one then would produce the most hydroxide ions, it would just be the example here. Since they all have the same ratio of 2 moles of hydroxide, it would just be the one that has the largest KSP value. Now that only works because they're all 1 to 2 ratio. In this example, they're not going to be a 1 to 2 ratio. So what I've done in advance, just to make this go a little bit quicker, is I have set up the KSP expression for all 3. So we are looking at 3 solids right now. We're looking at silver chloride, silver chromate, and silver phosphate. And we're looking for which of these is the molar solubility of silver higher. And so I've kind of fast forwarded a little bit here. I've plugged in my X values for our 2 ions. In the first example, it is a 1 to 1 ratio between silver ion and chloride ion. In the second salt, it is a 2 to 1 ratio between silver and chromate, and the third salt is 3 to 1. So let's look at our KSP expressions for the 3. Here I've plugged in the KSP. I have silver ion is represented by X, chloride is represented by X, and the KSP value 1.6 times 10 to the negative 10 would be equal to X squared. So in order to solve for the value of X, which is our molar solubility of silver here, I want to take the square root of both sides. And so here, X, which is the concentration of silver ions, is equal to the square root of 1.6 times 10 to the negative 10. And that value that I calculated earlier is 1.3 times 10 to the negative 5 moles per liter. In the next example, we know that silver is represented by 2x, so that'll also be squared according to the mole ratio, and chromate is just x. So 2x squared would be 4x squared times x would be equivalent to 4x cubed. I want to solve for x, so divide both sides by 4. And so now x cubed would be equal to, let's see, actually I don't know that I solved for that. If I fast forward here, I guess I gotta save some time. Just x, sorry about that. Looking at my notes from earlier, 4 would cancel here. And I solve for x has a value of 1.3 times 10 to the negative 4 moles per liter. Now, one thing I want you to think about is that the value of silver is actually 2x. And so I'm not looking for the value of just x, I'm looking for the value of 2x. So I'll take that times 2, and 2x, which is a concentration of silver ions, is 2.6 times 10 to the negative 4 moles per liter. So I'll need to compare those in a moment. In the last example, the concentration of silver ions is 3x. Concentration of phosphate ions is just 1x. And so when I simplify this in terms of x, 3x cubed is 27x cubed times x will be 27 times x to the 4th. And then to simplify that, divide both sides by 27. And just to kind of go quicker here, I have solved for the value of x. So, of course, I would have to divide by 27 and then take both sides to the 1/4 power, or to the power of 1 over 4. And so what I end up with for x is 1.6 times 10 to the negative 5 moles per liter. Since my value of silver is represented by 3x, excuse me, clean that up a little bit. 3x represents my concentration of silver ions, and that would be triple that value. So I get 4.8 times 10 to the negative 5 moles per liter. So what I'm doing now is I'm comparing those three values. Which one of those is the molar solubility of silver higher? 1.3 times 10 to the negative 5, 2.6 times 10 to the negative 4, or 4.8 times 10 to the negative 5. I think the answer is fairly straightforward. The largest value is 2.6 times 10 to the negative 4. So it is silver chromate has the highest concentration of silver ions. That's it. Thank you.